Hello, everybody. Really excited to be giving this talk. Really excited to be back in person. I came to this conference like pre-COVID, and it was a blast. I had a really good time. Just really like a little like intimidated and honored to be with all these people, all your people that are working on these open source projects. Like meeting all the core maintainers has been really exciting. So just a great environment. Yeah, so this is the setup a little bit. I have the links also over here. If you miss it, maybe you want to take a picture or something like that, let me know. We can always come back to it. But again, data you might want to download first. Everything else can go pretty quickly. So I'll wait for phones to be down. At least, no, I'll kill time with this slide up. So my name is Batorsky. I work at the Northeastern University at the Institute for Experiential AI. I've worked in a bunch of different settings in private industry and academia, in government. Basically every single setting that I've been in, I've done NLP because there's a wide availability of text data. Text data seems to be one of the largest sources that is there's always there. There's some text component of any sort of data set that you're working with, any sort of data set that I've worked with. So NLP is a really useful set of tools, and all of the open source community makes it so you can leverage kind of the state-of-the-art approaches pretty easily. So the Institute for Experiential AI, just a little bit of detail about that. That's sort of focus. There's a research and a kind of consulting component. I work more on the consulting side where I work with internal and external clients, sometimes on research projects, but most of the time on applications where we actually build a solution that's going to be useful for the client. But the idea is experiential AI is sort of human in the loop, understanding subject matter and getting subject matter experts involved and sort of feeding that knowledge back and forth between the application and the subject matter. So that's kind of the idea of it. So I'm going to move on from this slide. Hopefully people have taken that down. This is a slide with my face on it. So some motivation here. I love this visual. This is from Domo. They update it basically every year. There's just a massive amount of data that's being generated every minute of every day. There's 5.7 million Google searches. Slack people are sending 140K messages every minute, every day, which is a huge amount of data, right? And this is kind of a projection of like what that data volume kind of looks like. And it's just been kind of exponentially growing, particularly in the area of unstructured data. And unstructured data includes things like images and video, but also text. And that's what we're going to be sort of focused on here. So what is natural language? Does anybody want to take a stab at this? Self-explanatory, but maybe somebody wants to try it out. You can raise hands or shout it out.
How we speak.
Yeah. Any other attempts at that?
What are these humans actually use in contrast to programming languages?
I really appreciate that because you teed up exactly what the point that I was trying to make. So natural language is sort of self-explanatory. It's a language that developed naturally, and you can think of it exactly in opposition to, maybe not in opposition, but in comparison to computer language, which is a lot more structured. It has a flow. You can expect that if you run the same program, that it should have the same result, hopefully. Program. But language is a little bit less, a little bit fuzzier. There's a lot of long-term dependencies. It changes over time, right? The nature of language doesn't always obey the rules, and sometimes the subversions of the rules have meaning in itself. Think of negation and things like that. When you say this was good versus this is not good, very similar words, completely different meanings. So it has a different set of things that are need to be taken into account when you're thinking about them. I really like this visual of the progression of natural language processing. We moved from a very kind of tailored, small data kind of approach where there's a lot of emphasis on understanding language, and linguistics expertise was kind of built in. And now we've moved into this paradigm of deep learning where it's less transparent, but the need for machine learning expertise is higher, and the need for linguistic expertise has sort of like been pushed a little bit to the side. You can just expect the model to kind of understand these patterns. And not to say one is better than the other. We've made some decisions that have gotten us to this kind of world, and some of those decisions are worth considering and taking into account. actually, this talk is really interesting, but Goldberg, he says we should push towards using both expertise, both linguistics and machine learning expertise, which I think is an interesting kind of initiative. So now that we're in this like really big data, deep learning kind of world, we can do really kind of cool things. And this is HuggingFace's like just kind of showcase of transformer models, and just you can have them sort of write your own presentations for you, right? Where I say I'm a data scientist, and everything in bold is written by the model, right? The model decided just based on that context what to fill in, and it's words, right? It makes sense. It's legible. It's not very useful or informative, but it is like language, right? It has generated language. And then people have probably heard about this, DALL-E, or Stable Diffusion. It's like, I feel like I made this slide and then a month later there was Stable Diffusion, and then it's like open source. So everything has changed in like even in the past like few months, but basically just from combinations of representations of images and text, it's able to, given a prompt, create a pretty novel, interesting recreation of what you sort of specify in the text, right? An illustration of a baby daikon radish and a tutu walking a dog. Very specific, right? But it's all there, right? All the components are there. Yeah. So I think that's pretty amazing. But, and this is going to be always, there's going to be a comma but in like most of the things that I'm going to talk about today. The data is, whatever you put into your model has the same, is going to transplant its biases into your results, right? So this is from DALL-E, particularly example. If you put in like a flight attendant or a lawyer, you can see that there's some very specific stereotypes that the model has internalized. And how that shakes out may not be as obvious as this, but it's there. So more interactive here, right? So structured data, I'm going to give kind of a hand-wavy explanation of what structured data is. Conforms to a data model, has a consistent order, it's quantifiable. So then we have some examples of what structured data might be.
Table.
What?
A table.
A table.
Okay.
Oh, a table. Yeah, like the format, the data model. Yeah. So that's definitely one. Yeah. But like, what might be in the table? I guess is sort of what I was more thinking. Like what kind of like information might be structured versus not. Numeric, yeah.
So like the scale survey data, for example.
Yeah, right, like a Likert scale or something like that from 1 to 5, right? And so what's the difference between, let's take that example, Likert scale. Like what is the difference between something like a Likert scale and text data? Yeah, go ahead.
Yes, sort of a finite amount of values that you can have.
Right, and you know the order of them, right? They have an intrinsic kind of value in them. Text is not so simple like that, right? So if you think about like height, weight, you know that 12 inches in a foot, right? There's some conversion metrics. There's already value attached to it. In text, it's not so clear, right? Like what is the 3 times like the letter A? Like it's not clear that that's how it works. Also, one of the things I'm going to come back to a few different times is long-term dependencies. So it's the example is like, like Ben watched a movie, he didn't like it. He goes all the way back to the start of the sentence, right? And like being able to establish those long-term dependencies is a like, really tricky problem in text data. I'm gonna posit that this is sort of the purpose of NLP. This is kind of a working definition, so if you disagree, I definitely would love to hear your thoughts on it. But in like the perfect universe, you can have a perfect response to every input text, like a human might have, right? Like you have a call center, somebody's answering it. Maybe it not be perfect, but it's like, approximating like an optimal kind of response to the input. But you don't have an infinite call center, right? You have to create some kind of heuristics. So you need to be able to create some kind of informative representation to the text input. Use that representation for some purpose, right? Is it classification? Is it grouping? Is it anything like that? Is it similarity? Things like that. We're going to actually be using one particular like utilization. We're not going to vary the utilization in that we're going to be using a sentiment analysis task. But the thing that we're going to vary a lot is this informative representation. Does this make sense? Is this completely off the wall? Anybody want to complain about it right now? Yeah.
So, could there be like a more sort of like reach goal that's more like understanding language in some sense, as opposed to just giving an accurate response back?
Yeah, I think that's a really good point, right? I guess that's something that's missing here is the understanding. It's just the reaction that's sort of being focused on. Yeah, that's a really good point, and I think that's I think a lot of people are tackling that challenge, and we'll actually talk about it a little bit. I'm glad you mentioned that. That just internalizing patterns. If a model just internalizes patterns, it doesn't necessarily mean it understands anything. Cool. So I'm going to be giving an overview of basically all of this. So I know it seems a little intimidating, but what's going to happen is we're going to sort of give a survey over these. I'm not going to dive super deep into any particular topic. There'll also be code. Don't worry, code is coming. But we won't also be diving too deeply into the code itself. The idea is to give a survey of these approaches, how they sort of feed into each other, kind of the pros and cons of each, and what one tries to solve versus another. Try to get a conceptual understanding and a light touch on the code as well. I tried to cram a lot into this, and I definitely left a lot on the cutting room floor. But I think these are useful techniques and things that I can sort of drag a story through the entirety of it. I also have this like timed for like an hour-ish. I can fill up more time, but like definitely break in with questions if I'm going too fast or going too slow or anything like that throughout. That'll be great. Yes. Sorry. Thank you for reminding me. Yes, and I'll try to repeat the questions because otherwise I often forget that. Great. So the data set that we're going to be using is a review data set from IMDb. It's 50,000 reviews labeled for sentiment positive versus negative. Why this data set? It's for those reasons. It's easy to access. It's simple. It's pretty balanced. The passages are relatively clean. But the problem with that is that basically any problem that I've ever encountered is none of those things. So take that with a grain of salt. I also have particular feelings about sentiment analysis, just as a definition of generally, but it's a nice, clean objective. So we're going to use it. And also, I had extracted the titles, but like it's like kind of a random selection of titles for on IMDb. It's not like all like Star Wars and stuff like that. So it's unfortunately it's gonna be hard to like look at the words and be like, oh, I understand that review. These are the tools that we'll be using. Scikit-learn, NumFocus, thank you very much. spaCy, which is extremely powerful. I've done another talk on spaCy for NLP. It's an awesome library if you're really interested in digging into NLP. Highly recommend it. We're not going to use it for that much, but it is very useful. Transformers, which is also plugs in spaCy actually, which gives us access to kind of the cutting edge type models, and it has a really nice interface. And PyTorch for some deep learning applications that we're using. Okay, so let's get started. Start with the basics, right? You learn about the body. You start with like cells. You learn about text analysis. You start with tokens. So a token basically is defined as a useful semantic unit, and you can make a bunch of decisions about what is a useful semantic unit. A lot of those decisions in the more like cutting edge things, BERT makes a bunch of decisions about that tokenization. You don't even see it, but it's something that you should know happens underneath because it might change based on your different domain or if you have a different language. Yeah, actually an example of that is I worked in one research project that was using Chinese. And something that I didn't know about Chinese before I started working with it is there's not a clear definition of like white space, right? Or a clear definition of like, it's not always just like one character. It's not always individual characters. Sometimes it's multiple characters, and sometimes characters together mean something different from the characters individually. And so a lot of the tokenization strategies use kind of like a probabilistic approach where they're just like, well, these usually appear together, so we're going to split them like that. I don't know if people have other examples like that. I'm really always interested in hearing about other languages and how their tokenization like considerations are totally different from English. Anyone have an example English focused.
Wingding.
Wingdings. Yeah, I mean, like emojis would be one. Yeah, somebody asked a question about emojis last time I gave a talk, and I was like, I don't really know. Like, I don't know how you would process those actually. Yeah, so that's sort of like tokenization is one strategy you might want to think about. A lot of the times we're just going to be splitting on white space because it's simple. And then if you have multiple tokens in a row, you call that something like, if you have 2 tokens in a row, you call it a bigram. If you have 7 tokens in a row, you call it 7 grams, so on and so forth. So you can see with this example, I'm learning natural language processing. If you just look at the unigrams, you have every single sort of white space split token, and then bigrams and so on and so forth. Yeah, tokenization strategy is important. It's worth considering how your tokens are being split and whether those are the use cases. So, you know, half the presentation title is bagging. So this is essentially what bagging is. I have a lot of examples around football teams. I have no idea why. I don't really care about football. And I imagine that probably this is the wrong audience to have football references, but whatever, it's fun. Say you have these 2 different, we're gonna call them documents, right? I am a Patriots fan, I am a Giants fan. You are essentially doing the white space split, and then you're throwing all the individual tokens into a bag. And I have them specifically out of order because the point is these do not have order anymore once you start throwing them in that bag. And then say if you have only 2 documents, you can kind of arrange them in this idea of a document term matrix. And right now you have essentially a representation, our first kind of representation of a document, which is just the counts across the entire vocabulary. And because we added another document, because we have this document and these documents, there's only one difference of words, we already sort of are expanding our vocabulary. And we'll get back to that, how the dimensions sort of expand as you add more documents to your inventory. But that's sort of the bagging kind of mentality. And so this document term matrix or this word count, already we can start doing NLP on this. We already can start deriving some really useful information from here. So this is from Speech and Language Processing. The book is amazing and also free online, so highly recommend it. They use a lot of examples from Shakespeare and just like word counts and things like that from Shakespeare. And you have Shakespeare's comedies and Shakespeare's histories. And can anybody tell me, just from this word count, what they can maybe conclude or infer about the differences between comedies and histories? Sorry?
Different word choice.
Different word choice.
High frequency of certain words.
Yeah, right, exactly. So certain words like battle, like if a play contains a number of references to battle, you can probably be more confident if you're just comparing comedies and histories that it's a history, which is pretty cool. And like that's something that I'm not going to go into, but there's a bunch of sort of statistical measures that you can use, like a log likelihood, that can tell you, what are very like characteristic words of a particular category. And for that, you don't need BERT, you don't need fancy, deep learning. You just have it kind of out of the box. Does that make sense? Feel free to ask questions or disagree. I'm open to that. Great. To the notebook. All right, now I promised there'd be code, and so I'm going to make good on that promise. So is everybody able to pull this up? I don't know if folks are familiar with Colab. Has anybody been struggling at all? Is it kind of working? What you'll want to do also, and I should have mentioned this before because it takes a minute, is you're going to want to upload the reviews pickle file to your kind of workspace. And you want to do this for both of the different parts of the tutorial. Not hearing anybody complain, so I'm going to just keep going with it. So we're going to import a bunch of stuff. We're going to ignore caution here, throw caution to the wind. This is a bunch of code for just how I took the raw data set and turned it into the pickle file just for reference. We're going to make the label essentially, see, that's exactly what I mean. So we're just going to use this instead. So if you get a problem like that, that means Google Colab did a bad job of uploading the file. So you'll probably have to
I
go in.
specified the compression method and that error went away. So
Really?
you just have to have compression.
Okay, maybe that's the problem. Maybe that's the problem. I don't know. Last time I tried to run it, I just had to do this again. But whatever, we'll try it. Whatever. Either way, I have it up here, so we won't be held back. So we're just going to make the label just Boolean. If it's true, it's positive. If it's false, it's negative. It's just easier to use for that purpose. And now we're just going to look at just what our data set kind of looks like, because that's an important thing to do usually. So we have a negative review and we have a positive review. I don't know which movie this is, but I don't know, they didn't like it. Even though it had Alan Rickman and Evan Thomas, it's kind of surprising. But something that we can do with base Python is we can take our negative review and we can just apply a counter to its split just by nature on white space. And we get essentially a word count for that particular review, and that's just base Python and pretty easy to do. But we're going to be using scikit-learn just because it makes this really easy. And that's what I've always been using. And scikit-learn has a count vectorizer, which essentially does a similar thing. It does some has a bunch of defaults about how it's splitting tokens. So you would want to look into that if you are interested in doing a different tokenization strategy. But we're just using all of the defaults. We're fitting it to this individual review, and it's going to give us a sparse matrix out. You can, very easily just get this to an array, get the feature names from the vectorizer, and just kind of manipulate it, and essentially you can get the same thing back out. You can get a dictionary of words with their counts. Can anyone tell me what's different between this counter object and this dictionary that we produced? Or any differences that they observed? There's one particular difference I'm focused on, but maybe there's other ones. Yeah, go ahead.
Is it all lowercase, the second one?
It's all lowercase, yeah. That's exactly it. So one of the defaults, and this is just like a catch, one of the defaults is that lowercase is all your text, which is, useful in some cases. Some cases that might not be that useful. So for example, and I think there's a lowercase somewhere. Anyway, there's the capital is considered a different token than, there we go, the lowercase, yeah. Yeah, go ahead.
Question, and this might be getting a little bit ahead, but one thing I'm thinking, just looking at this data, and it's sort of relevant to my work also. You have names of people like Alan Rickman, Emma Thompson, for example, and in these cases, is there a way to identify names and to put them as bigrams in the document term matrix when you're analyzing it later?
That is a really great question. So the question was, is there a way to identify particular sets of tokens that should hang together in some way, like names or something like that, like Alan Rickman? And that is a whole sort of area called named entities, or we would call that a named entity because it's an entity that actually has like a real world. It's actually naming something. Like the whole set of tokens together is actually the name of something. Like New York City, right, is an example I always point to. Right, it's 3 different like white space split tokens, but they don't the individual units mean something different from them altogether. Not going to necessarily talk about that. I do have another talk that I talk about named entity recognition, so definitely recommend looking into that. But yeah, there are ways of approaching that. There's out-of-the-box models that do that kind of recognition problem. But yes, it is important to treat them as somewhat different from the individual. Like new on its own should be treated differently from New York City. Does that make sense? Okay. So the first thing I always like to do in any data science application that I do is do a deterministic approach because it's very easy. It'll be very quick, and sometimes maybe predicting the mean is what you want to do, right? Like that, maybe that's right. And it's good to set a baseline for your performance, right? How basically low can you go with the dumbest approach, right? So this deterministic approach is essentially just saying we have an inventory of positive words, we have an inventory of negative words, and we're just going to subtract the scores from each other and treat that as kind of a threshold, whether this is a positive or negative review. Very simple, and also this list of words is very, very tiny. There are smarter ways to do sentiment analysis where there's actually a larger inventory of words that are scored a little bit more informatively. Has anyone heard it, like used Vader, the Vader package? Hey, we got one person back in the day. It is very quick. One of the nice things is it just can score these words like that, right? Not very good, but it's quick, right? Sorry, I don't mean to. I think there's now more advanced sort of scoring that does. I don't want to throw that library under the bus. But yeah, so that's what we're doing here. We're also doing this train test split here, which we'll be using kind of throughout the entire thing. So this is also, we're going to look at both accuracy and the classification report, particularly looking at the F1 score. And we can already see that this doesn't do very well, but this sets a nice like baseline for us to start from. So now let's go with our count vectorizer. So now we're not going to just use the defaults. We're going to remove things that are called stop words. So things like and, the, but, words that we're assuming to be uninformative. Scikit-learn has a set of these already kind of inside of it. But, you know, you can always add additional stop words that you don't think are going to be that useful. We're also restricting the number of, our vocabulary only to words that appear in at least 1% of the entire corpus. Because if we don't, we have 80,000 unique tokens. And even with this reduction, we get, I forgot exactly how many, I have it somewhere, a few thousand tokens. So we're setting up our count vectorizer. I'm going to be using this pipeline functionality, which I think is awesome. But I'm also not going to really be explaining it. But essentially, all you need to know is that it can stitch different components of a scikit-learn pipeline together. Very highly recommend. We're going to use logistic regression, and essentially that's what we're going to be using throughout. Just fairly simple. I just found this ran a little bit easier and didn't complain as much, so I added higher max iterations. So we're going to run that. We're going to score it, and we're going to get a classification report out of it, and we're going to get. Oh, I need to update that number. We're going to get it doing very, very well. And spoiler, this is basically like we've topped out of performance with this approach. And there are like caveats and like good and bad to that. Like the point that I want to make is that even with a simple method, we're actually doing really, really well. Other caveat is that a lot of the other methods that we're going to be using, we're not going to be doing a lot of tuning to, and so they could probably go higher if we actually did more tuning to it. And that this model applied to something outside of the IMDb data set is probably not going to do as well because it's fit to a particular vocabulary. And that vocabulary size is, I believe it's something like, yeah, I think count. Let's say how large this vocabulary is. Oh, okay, it's not that large. I thought it was larger than that. 1,500 dimensions, essentially, to this input. And again, the representation here, I feel like it needs to keep coming back to the representation is word counts here. So each document is represented as a vector of word counts. So that's the representation. Our utilization of that representation is a logistic regression to classify positive or negative. Does that make sense? Too fast, too slow? Faster, slower? Just right? Perfect. Okay. I don't see any feedback at all, so I'm going to be, yeah, just right. Perfect. Great. So that is count vectors, word counts, rather. So we're going to just keep track of this and keep coming back to that representation. We have this document term matrix is our word count, and our F1 score is pretty good. But something that you might have noticed in those word counts is that every single word, instance of every single word is counted exactly the same. But we know if we're going to create informative representations that there are probably words that are more important or tokens that are more important to our problem than others, right? And so there might be a way of collapsing sort of uninformative tokens into one particular token. There might be stripping uninformative words like stop words, which we've already sort of done. But you also might want to kind of create a weighting regimen where you upweight words that are informative and downweight words that are uninformative. And one kind of very simple way of implementing that weighting is term frequency inverse document frequency. It sounds scary, but it's extremely simple. Term frequency we already have, right? It's the word counts that we've already done. Document frequency is how often a particular token appears across all the documents. And then if you just invert that document frequency value, you get very common words being downweighted and very uncommon words being upweighted. Simple as that, right? And you can see it. You can calculate it essentially by hand because it's just straightforward. In this expression, I am a fan of Patriots or Giants, whatever you like. We understand that I am a fan. Those tokens are not that informative because they're the same across both the documents, but the informative thing is the team. So just because of the nature of this very simplistic example, we just get Patriots and Giants weighted at just like 1. Each instance occurs once, and it just is weighted at 1. And fan we get down weighted by 0.5. That makes sense? Simple, easy. And then the thing that I want to bring home is I'm not going to really explain cosine similarity, but cosine similarity is a way of comparing these two vectors to each other. And if you just use the word count, the raw word count, these two word counts are scored as pretty close to each other. So higher means more similar, lower means less similar. But we know that Patriots fans and Giants fans are very different. So we want to make sure that that is represented in our data. And so TF-IDF vectors are less similar than the word count vectors. Does that make sense? Any questions there? Hearing none, move on to the notebook. Back to the notebook. So TF-IDF, this is just almost the exact same example I just gave, where the movie is shared across all of these different documents, and it's just the, what is the actual adjudication at the end that matters. And if you do count vector, it treats everything the same. If you do TF-IDF vectorizer, you get the words that are pretty common down-weighted. So I kind of am being like iffy with language here by saying there's like separability, better separability. It's not like true, right? Because this in this count in these count vectors we have 1s and 0s, right? Like it appears or it doesn't appear, so it's actually just like the same amount of separability. But you can imagine that if you want to create this informative representation, you want that representation to contain more information of what's informative. So separability may not be the right word, but you can sort of see it's doing what we expect it to do. And then we can just plug the TF-IDF. So there's a count vectorizer, there's a TF-IDF vectorizer that operates sort of in the same principle. We can plug that into our pipeline, and then we can get results. And the results are like comparable. It's like this, almost the same as the count vectorizer. What is nice is maybe we saw a little bit of a bump in the recall, small bump in the recall, and I guess I don't need to go into all of this, but this was just a way that I kind of wanted to do of looking at the different actually coefficients in the logistic regression for these different terms in the vocabulary, just to show what is the difference between like how much the model that's trained on TF-IDF works versus the model that's trained on count vectors, and just to show that like, yeah, I mean I'm not gonna go through all the code, but the model is essentially learning more from the word bad for TF-IDF than it is from the count vector, just by how the magnitude of the coefficients. Yeah, the idea that like bad is a important word that we expect that the model will use to identify whether it's a positive or negative review. But right, because language is complex, maybe the use of the word bad is, it could be badass, right, or something like that. I don't know if they're going to censor that. Yeah, I feel like that's sort of what I wanted to look at. I have some other code here for like if you want to compare what the difference is. Does that all make sense? Yeah.
Just wondering with the inverse document frequency, if you ever weight it differently, square the inverse, mark that difference.
Yeah. So the question is, have you ever done any different transformations to that weighting? I haven't. That's an interesting idea. Yeah, I mean, it's, TF-IDF is just a way of weighting, of like, it comes from a field of information extraction, or information retrieval rather, where the idea is you're trying to get the most informative information out of the text. So yeah, that'd be interesting. I wonder what would come out. Any other thoughts, questions, complaints? Yeah.
So based on the table above, we can get a sense of which words are more predictive of positive versus negative.
Yeah, it's a little bit like I got myself into trouble because I was just doing this as kind of an exploration, but essentially it's just kind of looking at the magnitude of the coefficients, just using that as a proxy of how much the model is relying on that for its prediction. And this is kind of a ranking, and so the TF-IDF ranks bad as more informative.
It's ranking.
It's a ranking. Yeah, sorry, that's why I just like kind of glossed over it, and that's why I'm getting myself into trouble. But this is like a very simple like comparison. It's not necessarily what I recommend you do, and it makes like statistical sense. Yeah, go ahead.
Did you do any spell checking or normalization?
No, yeah, no spell checking, no normalizing to this. If you want to mess around with the data, you'll see that there's like some like kind of garbage tokens in there. It's pretty clean, but if you actually, I spent a lot of my career doing web scraping, and I have like PTSD from that because you'll have that problem, like, and it's almost like intractable to like get rid of all of the garbage. But yeah.
Does it change anything if you like lematize it or try to go to like the root word and?
Yeah, so the question is, does it change anything if you do any lemmatization? So it's a similar sort of question where like more normalization of the individual tokens. I haven't tried it, but yeah, usually you will get that, and like it's like a nice pre-processing step. So lemmatization is is essentially what I was referring to, like here, where I am and I will, the sort of root form of will and am is B, so you can turn everything to B, and then you get the counts for B rather than the counts for am, will, and B separately. And so yeah, it probably would help the model to some degree, but yeah, it's worth. There's a bunch of pre-processing, again, a bunch of stuff that I'm not going into. There's a bunch of pre-processing stuff, and I don't know if I have a good reference of like a set of things to do. The spaCy is really useful for that, because spaCy has a lot of like attributes to individual tokens that you can use for your pre-processing. So I don't know if that's a useful answer to your question.
I'm more just curious on your, what's your experience been and what the outcomes, if that pre-processing stuff is worth it. And
I mean, I think the pre-processing is almost free, so it makes sense to do it and try it anyway. Yeah, I mean, the stop words for sure. I've seen better results with that. Though there's always like it depends kind of thing, where if you're dealing with like text and sequence, right? If you actually do have can maintain the order, I've seen applications where they are like running like a recurrent model. Spoiler, running a recurrent model, and they remove stop words, and it's like, why would you ever do that, right? Because the stop words carry information, and particularly the context in which they appear carry information. And bagging, I can sort of understand it because you want to like condense the vocabulary, but it's not always the right thing to do. That was a long-winded answer to your question, but yes, it's worth trying because it's not hard to implement, especially with the tools. Thank you, open source, especially with the tools that are out there. It's pretty easy. Cool. So here's our progress so far. We haven't gone too far. But this is something I sort of made reference to before, that our vocabulary expands as we add more documents to it, right? If we just took just this subset of literature, we get like thousands of unique words, right? I put in Shakespeare's play because we were using examples from Shakespeare, but Shakespeare's play has a lot of words as well, a lot of unique words as well. So anybody want to explain what the cursor dimensionality is? Mainly asking so I can take a drink of water.
And the number of features grows very quickly in this.
Yeah, when it grows too, yeah, when it gets to sort of the number of features outgrows the number of observations. Essentially, you can have your model, for example, just memorize the data exactly, which might be useful for that approach, but not always. So, does anybody have like tools that they use to combat the curse of dimensionality? I feel like the curse of dimensionality is such like a dramatic term. It's like curse. But how do people fight this curse?
Clustering.
Clustering? Yeah, clustering is one approach. Does anybody have other approaches?
And word to that.
Word to vec? Yeah. I mean, spoiler, but yes. Yeah. That would,
So when you set some kind of a threshold, if it appears more than
yeah. So that's what we've been using. That like min df keyword is useful. I guess maybe it's a simpler question than I'm asking. Is sort of dimensionality reduction is one approach, right? And that's essentially what we're going to get into here when we talk about topic models. And the idea of a topic model is that essentially every document is composed of a set of different topics, and those topics themselves are composed of a set of different words. And how this is operationalized is essentially just like dimensionality reduction, right? Single vector decomposition. One of the ones that we're going to be using is matrix factorization, non-negative matrix factorization, which I find works really, really well. David Blay has a really interesting, I think this is actually the article, the 2012 article, where he talks about, no, it's an older article, about latent Dirichlet allocation, which is another approach. But we're going to be doing non-negative matrix factorization because it's faster and sometimes works better. But the idea is you want to reduce the number of dimensions without losing a lot of information. And those dimensions, those latent dimensions that you extract, we're calling topics in this world, right? That's topic models. This is just a visual that I like. It sets up something later. So say you have your data in 2 dimensions. You can extract dimensions that better explain the variability in the data. This is not that impressive when you go from 2 dimensions to 2 dimensions, but if you have, for example, 1,500 dimensions, like 1,500 different tokens, it's a lot more impressive to go down to 2 dimensions. This might be more exciting to folks. Like this is an example that we actually used in real life. Yes, you can use NLP in real life. I worked on a B2B company where we had these small businesses that didn't fall neatly into any particular category because those categories tend to be fit to larger companies. So this is an example near where I live, where it's a yoga studio that also has a health food store and also has a restaurant in it. So it doesn't really fall into any one of these categories. And we were thinking that, well, that's probably true for a lot of these businesses. These businesses kind of straddle a few different categories. So could we create more kind of nuanced representation of what is the content of that business? What is that business doing? And one approach to that is doing these topic models. And I really like the visual in the middle here it's called a termite plot, I believe, where essentially we're visualizing each 3 of the topics that were extracted from the topic model and the relevance of a particular word to that topic. So all of the words have some loading on each of the topics, but certain words load more heavily on particular topics. And just by looking at this, somebody looking at this, what could you maybe tell me about one of these topics?
Topic 3 is food.
Topic 3 is food. Why do you say
We
that?
see that, you can see the concentration in the chart, right? Catering, day is noise, but food, menu, pizza.
Exactly. Yeah. So again, so something that I should mention that these models don't give you out of the box like what the topic is about. It's sort of a top-down decision, and so that it injects its own amount of noise, and you might see patterns that may not actually be there. But what's nice about this is you get like a nice interpretable kind of understanding of like what. In a lot of ways, these are pretty clear topics. I'm cherry picking a little bit what are the topics and what are the words that I'm showing, but this is easy to sort of share with somebody that has no familiarity with what are the underlying mechanisms. And then you can get every single business kind of represented, right? Each business considered as a document represented across these different topics. So the representation we're doing in this case is going to be these topic vectors. Any questions there? Yeah, go ahead.
Yeah, it's something that I messed with ages ago, and I'm curious, how do you tune the number of topics? Because that's always first.
Yeah. So the question is, how do you tune the number of topics? And the answer is, I'm not sure. The answer is you tune it until that. So that's the catch about this, is an unsupervised kind of approach, where you are going to, I got a question similar to this, right? Like, if the topics are useful for your model, then they are useful, right? Like, for whatever your downstream application is, if it's yielding good results, then that is the number of topics you should use, right? And you can always like tune these and play around with it, with like this pipe, like say you set up this pipeline, and you can see the performance if you try different numbers of topics, right? So you can tune that a little bit. But again, it's like a, it's like a fuzzy kind of like art thing, less than a particular science. Yeah, but right. Sorry, I should also say that in these topic models, you're usually picking the number of topics you expect to come out. So it's kind of a hard decision to make. I just arbitrarily choose 10, just because it's a nice number. And that's what I'm going to do here. So we're back here. I have this useful utility for just displaying the important words for a particular concept, topic. And so I'm choosing just 10 components. I'm setting up the non-negative matrix factorization with some just things that make it work a little better. NMF likes TF-IDF vectors to be put into it. It likes to be fit on TF-IDF vectors rather than count vectors. I used to know why, and now I don't. Yes, for some reason it seems to work better with that. And then if we're gonna apply this display components to it, you'll actually see something useful come out of it. Probably should have just not run it right now. But what you'll see is it'll give you the top set of words that are most relevant to that topic. And if it ever finishes, you can see this. Does anybody see anything interesting about these topics?
Topic 9 is comedy related.
Yeah, it seems to be right. It seems like comedy related. The top words are relevant. Topic 9 is comedy. Yeah.
1 and 3 should be the same.
Yeah, 1 and 3 should be the same. Yeah, I have a hard time understanding those ones.
But what if it's about the movie Saw?
It could be. But then that probably would be. So the other one that I thought was particularly interesting is this one, this topic 7, that is horror and gore. Yeah, budget effects maybe less. So it's it's not a perfect decomposition here. But if we look at the, so remember that out of this we get a representation across all the topics for each individual document, each individual review. And say we sort these reviews by their particular loading, like how much that particular topic is relevant to that review. If we sort them and just look at the top ones for this topic 7, we get horror reviews for horror movies. Now, this is the top 2, right? If we went further down, we might not see as clean an example, but this is a fairly easy model to fit, and you get some useful stuff out of it. So we're going to essentially do the same thing as we did before, except this time we're going to use NMF, and we're going to set up that pipeline, and here's the result of it. But the accuracy is worse. But remember, we're going from 1,500 dimensions to 10, so for sure we're losing some amount of information, and we haven't really done much in the way of tuning. And actually, if you add a little bit, like a smaller set of like text features, this is if we just like subset the actual TF-IDF to just the words that appear in at least 5% of documents, you get a bump in performance. That's pretty nice. So things need to be tuned a little bit. I'm not saying that like topic model is just going to beat all these other things, but you do get something interpretable out of it. It's useful for understanding what are relevant words, and useful as like a thing in the loop of building these things. Any questions there?
This is more of a maybe a technical question, but this seems very similar to PCA, like principal component analysis. Is it just that, or is it more to it than
Yeah, so like PCA, operationalization PCA is latent semantic indexing, which is another, it's not really like a topic model because they're not like additive, the different components, but you can do, there's a lot of examples of using latent semantic indexing for reducing the dimensionality of text counts, word counts. So yes, yeah. Non-negative factorization doesn't have to be applied to text, right? It's just, it's nice because it's the thing that I didn't really like to talk about or glossed over is essentially you get these additive components. So each topic is, the loading is positive, right? It's harder to understand if a topic loading is negative, right? Because like, what is that? It's less horror-y, like it's hard to understand that. All right, hearing no other questions, I'm gonna move right along to, we have the spoiler over there. So this was just teeing up this visual just keyed up this point, right? So you have these nice topic vectors. They explain your data really, really well. You're very, very happy, and then you get more data. And you're like, dang. So now it doesn't explain your data quite as well. And so what you might do is, fit another topic model. You might do this iteratively. You might put like a ton of data together and fit the best and greatest topic model. And essentially what you would be doing in that case is getting into this area that is sort of referred to as transfer learning, where essentially you want to learn a set of topics that is generally applicable across all text ever. And spoiler, we're not going to be using the topic model paradigm for this, but you could, right? You could just you could try and fit the best topic model that explains all text ever. It's probably going to be a very hard task. So it's going to be operationalized a little bit differently. But what transfer learning is essentially just kind of traditional machine learning. You take your task and you put it through your learning system, take another task, put it through your learning system. But for sure, there are shared elements of the data and shared elements of the task that you might be able to, if you put your data together, get some representation of knowledge, and then pass that to your next learning system to sort of boost it, to give it some more juice. I love this visual. This visual is like, I feel like it's so an primitive way of explaining it. And so what we're going to use as our source task in this case, rather than like topic modeling, is we're going to use term co-occurrence statistics. And this, there's a ton you can do with how often a word occurs with another word. And basically there's some people that argue that this is all of modern NLP, is just, different operationalizations of term co-occurrence, which is true in a way. But this again comes from the speech and language processing, looking at, instead of a document term matrix, we're looking at term matrix. It's how often two terms appear together in corpus. And just looking at this, what can you tell about the relationship between Pi and Cherry versus Pi and digital? They occur together more often. Now, what might that tell you about it? That the fact that they are more often in the company of each other. Yeah, what would that like? What does that sort of bring to mind? Like, what does that make you think? They're related, right? That there's some relationship between the two that makes it more likely that they occur together than, for example, Pi with digital or Pi with another term. Unless you're working with like Raspberry Pi or something like that. This is a different corpus or something. But right. So, and you could say you already have kind of informative representation of each individual token here. And here we're actually going to be talking about representations for individual tokens, individual words. And so you could actually say like this is like a vector that describes this word to some degree. But it's a little bit hard. You get into that same problem where you have every single different word, you get a huge dimensional vector. And so it probably makes sense to fit a model to this co-occurrence statistics. And there's this distributional hypothesis that kind of governs this kind of thinking, that a word, you can say that a word is related because they occur together. And so there's a couple of different approaches to this. There's more than this, but Word2Vec, which is used as a neural model based on these co-occurrence information, and then Glove, which uses the co-occurrence statistics themselves to create these representations. And the idea is you're going to have your model learn a numerical vector for each word based on its context. And those individual dimensions are not readily interpretable. They just do a good job of representing the patterns, the co-occurrence information of that particular word in context of other words. And so the canonical example is that the distance between the vector for king and queen is the same as the distance between the vector for man and woman. And that makes intuitive sense, right? That makes meaning sense in our minds, but that's not necessarily what this is fit to. So this is the caveat, comma, but just because it's all fit to co-occurrence statistics. Co-occurrence says something about meaning. It is not meaning. It is not the same thing as meaning. So these vectors, I say this because when I first learned, when I was young and fresh, and I first learned about these word embeddings, I was like, oh, it understands the meaning. This is a representation of meaning. It's not. It's a representation of co-occurrence. So those two things are different. But it's still super powerful, right? Because by this representation carries with it some information that we can do that is useful for understanding the relationship to other words and what it can be, where it's used, how it's being used. Pretty cool. Any questions on that? I know there's one slide on all of word embedding, so it's a little bit.
Maybe this is a bit philosophical, but what would you consider a system that would capture meaning to look like?
Yeah, what would I consider a system that would capture meaning? Yeah, I don't know. It's a good question. Yeah, I mean, co-occurrence is a good proxy for meaning, right? But it's not necessarily, I guess I struggle with it. I'm not sure if I have a clear answer to that question. I don't know if a system, I feel like a system like that would have to build in a lot of linguistics information. This is just saying, find a pattern, represent that pattern, right? It's not, there's no boundaries on that. There's no, if you just fit it to just the giant data set, what is the data set that's going into it, right? Because it'll have a very different representation if you give it a bunch of biological text versus a bunch of random Reddit posts, right? And so, I don't know if that's really that useful, but a system would have to build in more of what we use, right, when we're learning language, right, where we would understand what a certain particular context works with, what the modifiers on those contexts are, and sort of bounds the space a little bit more than just extracts patterns. Oof. I don't know. That was a hard question. Thank you for that question, but I don't know if that was a satisfactory answer. Cool. So you also get other cool spatial characteristics from this. I really like this talk. It was really interesting. Time flies. But this is basically taking the word embedding algorithm and training it on job postings. And does anybody see, can anybody characterize these little boxes of words, what they might be, knowing that we've all looked at job postings before? I think these were technical job postings too, right? Yeah, these are technical job postings. Does anybody, so what would you describe this red box as, these words here?
Yeah, skills or competence.
Yeah, skills and competencies, yeah. Yeah, and then there's sort of the requirements, the job requirements and things like that. So so just by decomposing into two dimensions, right, you have these vectors that can be these word embeddings, which can be a number of different dimensions, but a lot of the times they're 200 dimensions, and then you collapse it to 2 dimensions, and you can see a lot of the spatial relationships just there. Really interesting talk, Mariam Jeshani. And comma but, right? This is considerations when using these embeddings that they will also build in the bias of the data that you feed them. I think this visual is really cool because it talks about how gendered, I'll try to explain this in an easy way, how gendered the actual representations of these words are. And there's kind of a shift that happens around the 1960s in the genderedness of language that sort of coincides with a lot of the women's rights movements, which you can imagine sort of changed the reference, changed how language was being used, particularly around gender. And you can see like a very strong correlation up until the 60s, and then that correlation kind of weakens in the later years, which is cool, right? You can just sort of kind of see this. But just all that to say that like your whatever text, what I was saying before, that if you put in like a bunch of random internet text, you get everything that the internet is, which is some good stuff and some bad stuff, you know, open source and then everything else. So it's worth considering what that means. Word embeddings, let's do it. So for word vectors, we're going to use spaCy just because it gives easy access to the glove vectors. If you're running this in the notebook, you will need to download this. You need to run this. Yeah, go ahead.
Is there any support in LTK for it?
Oh, I don't know. I'm not sure. I haven't really used NLTK for a while.
Okay.
Yeah, but NLTK is another NLP package. Is also really powerful. I just don't know much about it. But the only like spaCy a little heavyweight, but like you can also access the glove vectors themselves, and you can process them and do all that stuff. This is easier for me. Here is a bunch of code that I'm not really going to explain, where it's essentially just a kind of simpler way of turning a document into a single embedding. And what we're doing is we're just averaging all of the word embeddings in a document into one vector, which is, you know, hacky and probably loses a lot of information. But what we want to get is that document level representation that we can just plug into our classifier. So again, untuned, right? We're just doing kind of a simple approach. Yeah, but
This might be kind of a dumb question, but in general, how do you approach the problem of like when to make your own class for vectorizer rather than using boiler?
oh yeah, I'm not sure. Yeah, so yeah, I guess if I don't see a transformer that a scikit-learn transformer that does what I want it to do, I will just make my own. And they're not too complicated to make. It's just you got to fit it into its syntax of fit transform. It's not too complicated.
Like do what you want to do. How do you improve, like evaluate that? Or like what's the threshold at which you would like
Do my own.
a cookie cutter one versus like a minor?
Oh yeah, I mean, good question. So asking about when do I decide to build my own transformer, and I guess yeah, I don't know if I have like a rule or a heuristic for that. I mean, I didn't see anything that did something like this in scikit-learn, so I just did it myself. The reason I like tease it out like this, it's faster to do it this way than to shove everything through spaCy and have it process each individual document. In this case, it's taking the vocabulary that I fit to the text, turning each of those words into a word embedding, and then just multiplying the word counts by them. It's something that I've done before, and like I didn't used to do it in this format, in like a scikit-learn transformer format, but I've more recently discovered how powerful the pipeline piece is. So that's why. Sorry, I don't know if that's it.
Yeah, so thank you for explaining the rationale.
So yeah, so I'm just using that transformer and creating a document level representation. And our performance is, sorry, I shouldn't rerun it, but our performance is not bad, right? We've gone from 1,500 dimensions to 200 dimensions. We didn't do too much tuning besides just taking the average of an entire document's word embeddings. And we got, you know, F1 score of 84. Not bad. Still not 87, right? But yeah, still not 87. It's possible that this might be a little bit more generalized approach. So where are we at now? Gosh, time flies. Okay. So we might need to just jump ahead to the interesting stuff. So we're going to actually leave the bagging regimen, and we're going to talk about one of the things that we are missing from all of our representations. If we're throwing everything to bag, right? We're decontextualizing all of the language, even with the word vectors, right? Word vectors have general representations of a word's context, but not the specific context in which we find the word. So this is funny. I don't know, I'm just gonna explain the joke, right? So it's the same spelling and pronunciation, it's a different meaning, right? Because, you know, well can mean condition of well and also wishing well. And it's all about context to understand which kind of well should be represented in the system. Yes. So there's a bunch of different ways that we can represent context. We don't necessarily need to plug it into the latest and greatest neural net model, right? We can always just have like a window around each individual word and do things like that. You know, we can say, you know, concatenate different embeddings together, or average, you know, bigrams of embeddings and things like that. You don't necessarily need to jump to the, you know, the end with neural models. The question before about named entity recognition, right? You can do work to ensure that that when new occurs with New York, that it's represented differently than just new on its own. A bunch of stuff you can do around that. But we're not going to do any of that. We're just going to go to neural nets, because I decided to have one slide on all of recurrent models. You can let me know if this actually works, but I'm going to try to describe this kind of conceptually, right, and why this is a useful representation, or a useful representation to use in this context. So the idea of a recurrent neural network is it's sort of built for this kind of sequential data, where as the model sort of scans across the sequence, it carries with it some information from the beginning of the sequence. And I really love this visual because I think it gets at a couple of different things. It shows you that at the end of this sentence, you have a representation that has some contextual information from the entire sequence. What it also shows you is that the beginning of the sequence is kind of underrepresented by the end of the sequence. And that's a problem, right? Because that long-term dependency problem that I referred to ages ago now, where, you know, Ben watched a movie, he didn't like it. When you get to he in this model, you're going to have a very small contribution of Ben, me, to that representation at the word he. But honestly, you want more representation of Ben, right? Because it's informative to what he means. But sorry, I kind of breezed through that explanation. Hopefully that makes sense. But one way of dealing with that is these long short-term memory networks, which essentially incorporate ways of upweighting certain information and downweighting other information, losing certain information and remembering other information that is useful for the representation further down the line. And remember that problem of long-term dependency, because it comes back. Does this make sense? I know this is one slide on all recurrent models, and I apologize that there's not more. So to the notebooks, we're gonna just go for it. So if you're actually following along at home or somewhere, you might want to change your runtime type to GPU in Colab, because it'll run a lot faster. You can run it not on GPU, it'll just take longer. This is a massive block of code that I am not an expert deep learning engineer. So this probably is not the best way to do it, but it is a way of building a fairly simple LSTM model. Very briefly, this model will have essentially a word embedding, but that word embedding is a little, it's similar to like the word embeddings that we've been using, but it's not kind of trained for general contextual representation. It's trained for the purpose of this sentiment analysis. So you could slice out this word embeddings and use it for some purpose, but it probably wouldn't be as useful as like a glove embedding. But the idea is the same. The model is going to learn a representation of individual tokens. LSTM, this is doing all the work. We have some dimensionality of the input that's going to come into it. We have some hidden representation that goes as the model sort of scans across the sequence. And then essentially we basically have logistic regression. Yeah.
The embeddings, this is creation the embeddings from the data you're providing rather than actually looking up in
pre-trained embeddings.
Right. Yeah, but you can. It's really simple to say you have a pre-trained embedding and tell the model, and actually it would help it, right? Because the model has to now learn. Oh, sorry. The question was these are not reading in pre-trained embeddings; these are learning embeddings. So it's learning embeddings and learning the classification. So you might actually be helped by using a pre-trained embedding. This takes the classification of the final output of the LSTM. You get a representation of each step in the sequence, though, which you can do stuff with. But in this case, you're just taking the last step. So that, like this, essentially. Taking that and classifying that. Wait, where am I? I'm over here. This is a bunch of code to kind of engineer it so that it works well with the model. We're going from documents to token indices in the vocabulary. And we're also, you'll notice, subsetting it to just the first 200 tokens in the review, which is problematic, right? There's probably a lot more information to maintain. Actually, in the word embeddings, we're doing better, right? Because we're using all of the tokens that are in the review. And then this is a lot of stuff that is additionally happening to process it and turn it into something that can be ingested to the PyTorch training. I'm trying to think if there's anything I want to call out here. I'm using TF-IDF vectorizer here just to get the vocabulary. It's just, I don't know, it's an easy way that I was thinking to get the vocabulary out of it and to also get the tokenizer out of it, which will enable me to look up in the vocabulary the index of the term. And then there's a bunch of model parameters that I don't have a particular opinion. These are things that I've seen used, the hidden dimension of 512 and embedding dimension of 400. Doesn't necessarily need to be that. Output size, in this case, I've found it works better, or it makes more sense to use it for this binary classification as output size 1, because we just want a prediction of is it positive or not. And if it's not, it's negative, rather than 2 classes. I think you could probably make this 2 classes, but I didn't. Then a bunch of work happens here in terms of doing the training. I am using, I'm printing the loss for validation based on the test set. Don't do that. I think probably there's a lot of tutorials today that will do the same thing, where it's just like, whatever, we have 2 splits, but you want a different validation set than your test set usually. This is just training it for 1 epoch. And if you run it, it should run pretty quickly for 1 epoch. You won't see, you may not see as good results as we can get if we train it for longer, but just from 1 epoch, you'll get something like 82, accuracy of 82, an F1 score of like 83. So pretty comparable to our word embeddings without much additional tuning or work around it.
What's your sequence?
What?
Sequence length?
Sequence length is 200. So it's 200 tokens.
Is there any best way to choose that?
I mean, it's based on your data. Like, these reviews are actually pretty long on average. Some of them are really long. If you're dealing with like sentences or something like that, you don't need a 200 length sequence, right? So it depends. And like sometimes you might want to, there's some functionality to like turn them into individual, like split them up essentially rather than just like truncate them. But yeah.
Yeah, I'm just curious, is PyTorch the norm in the community now, or is the PyTorch versus TensorFlow?
I like PyTorch only because I like the syntax in HuggingFace's transformers library for PyTorch rather than TensorFlow. It's just, I don't know, it makes more sense to me.
It's fine.
Yeah, I don't, yeah. I'm not like heavy duty deep learning engineer, right? So I don't have to wrestle with this too much. But PyTorch, no, I like PyTorch. Cool. What are we at in terms of time? Whew, shoot. Okay, so we're gonna in like 10 minutes describe all of transformers. So one of the main issues, spoiler, of recurrent neural networks is they still have a hard time with these long passages. And they're harder to train, right? They're harder to parallelize. One solution to that is, so this is just an example of long-term dependencies, is introduced as the idea of attention, right? So if I'm giving this example of Ben watched the movie today, he didn't like it, you can imagine that the representation for he should have some, should carry with it some information about the word Ben, right? Like I've sort of referenced this before. Attention kind of operationalizes that more directly, right? Each individual token has some weighting of importance on the representations for other tokens. And that's essentially all of what attention does. It's trying to sort of mimic our own process with language, where we know when we're looking at he, we know where to look back to. We know just intrinsically where that reference is in the document. It's trying to teach the model to do that same thing. And this is a visualization of those weights, the intensity of those weights. And I'm curating a little bit because there's a bunch of different, attention weights, and usually different layers to that. But this is a very clear example. This is sort of BERT syntax, essentially, where it'll have a classification token, which is usually used for classification, has an attention to all of the tokens, and separation, which is like the end of the sequence. Now I'm going to explain all of transformer models in one slide. So again, I'm glossing over a lot. So there's an entire world of encoder-decoder models, which I haven't even touched on. But this is a adaptation of that to really leverage the power of attention. And the things that are most important to kind of understand is that the encoder takes inputs, all of the inputs for the entire sequence, creates intention across that entire sequence, has an output of the encoded output that goes into the decoder. The decoder takes its current state, what it has currently decoded, and that encoder representation, and outputs an output. Whether that's like another sequence, like translation or something like that, from English to French or something. And so what's important to understand about that is the only information about the position of the individual tokens comes from that positional encoding. So you can do like a lot of, you can do parallelization. It makes it easier to parallelize. It doesn't sort of depend on the previous states. But the decoder, the example that what I'm going to be focusing on here is something that's called a language model. And the language model objective is to predict the next word, right? So in that sort of paradigm, the decoder can't be able to see the rest of the sequence, right? Because otherwise the decoder would just predict the rest of the sequence, right? It already has it. So it's sort of blinded, like going forward in the future states. And you can understand that, it's a blind spot that maybe makes the model a little bit weaker. Like that probably you want that the strength of this encoding is that it has the entire sequence all at once. It can consider everything sort of at once, which is pretty powerful. But with the vanilla transformer, it doesn't in the decoder step. It doesn't have the entire sequence. The only reason I spend some time explaining that is because that is the difference essentially between a vanilla transformer and BERT. Where BERT is encoder only. It sees the entire sequence at once. But to get around the fact that it's now seeing everything and it has to predict something in that sequence, it replaces some portion of the tokens that are input into it with a special mask token or with a random token. And then the objective is for the model to predict that replaced token. So it's a similar thing to this language. It's the same idea. It's still a language model. But in this case, it doesn't have to do special blinding to one aspect of it. And it is solely an encoder. It doesn't have the decoder component. So it's simplified and has the full view over the entire sequence. How did I do? That was 2 years of NLP. 2 years, 3 years, something like that. A number of years. Yeah, so there's a conceptual understanding. There's a lot of modulo, a bunch of like fancy math stuff that happens, but conceptually, I feel like that explains it. Wow. Okay, so we're coming very close to the end. I will just sort of leave with this last piece. BERT, you will, in the notebook, you will install the transformers. You will load a pipeline that's called sentiment analysis that does a bunch of truncation and padding for you. You will apply it. I just apply it to 50 of them to make it doable, and you will get an incredible performance. Congratulations, you are now state-of-the-art NLP developers. And the reason I say that kind of tongue-in-cheek is because, like, this is, we've gotten 0.88 versus 0.87 from the beginning of the talk, right? Yeah, so you don't need to jump to BERT. BERT is not always like just plugging in BERT doesn't necessarily make sense. It's a lot of complexity that you're adding onto it, and it may not get you that much. And furthermore, because of the amazing open source community, it's this easy to use BERT, right? Now, something I didn't really get to is some stuff at the bottom where you probably want to tune BERT to your context. But again, you get marginal improvements. So that kind of concludes it. I have some just general advice, which is sort of what I've been saying the entire time, which you want to start simple, makes you better able to understand your use case, your data, all that stuff, and then add complexity rather than go like BERT all the way, because it's the latest and greatest. Right? And that's it. A bunch of interesting materials there. Feel free to get in touch. If you're interested in Institute, also get in touch or get in touch with them. But I will take, any questions for remaining time.
That's first.
Is there a lighter version of BERT?
A lighter version of BERT? Yeah. So actually, the out-of-the-box sentiment analysis pipeline in HuggingFace is using a thing called distill BERT, which is a lighter version of BERT. It is just less memory intensive. It has it's essentially distilled the information that BERT has into a smaller.
So it's called
Distill BERT, yeah.
but it's not a default when you install it.
No, you can. Yeah, you have access to it with the Transformers library. You have access to all these different models, and distill BERT is just one structure of making it lighter. There's a bunch out there.
So how's the explainability on BERT or something like that? I mean, because you showed it so nicely with logistic right at the beginning, right? We get a coefficient weight that goes to each one. How do we know what's happening with BERT?
Yeah, I feel like you don't. You get representation, if you peel off that classification layer, you do get representation for each individual token that is contextualized. So well, right, like the word well would be a different representation in the context of wishing well versus I am doing well. Compare that to word embeddings. So really cool stuff you can do with that. You can say how similar these two words are with the contextual information. And then you can interpret that to mean something, to have some meaning in this. But but dimensions themselves, again, don't have a readily interpretable meaning. There's 750 or something dimensions that you get out of the representation. So I think there's a bunch of work. I'm not too familiar with it, with using these, interpreting what these, how these models are coming to the decision that they're coming to. But that's sort of, assuming that this model has learned stuff that is valuable, we can interpret what that value is. And that's kind of an interesting approach. Sorry if that's not a very satisfying answer to your question.
There's always more to explore with NLP.
Yeah, it changes. Probably half the stuff is now wrong in the past month. Yeah, I'm back.
I've got so many questions.
Whatever. We can.
Do you feel like NLP? So do you feel like this coexists with name image recognition? Would you do your name image recognition first and then move on to how would you organize?
I would say it depends on what your use case is. If you're interested in seeing the a person tracking people or tracking places, and say if you're looking at product reviews and you want to see if people mention a particular product, you might want to just focus on named entity recognition. Throwing BERT in there is it's going to get you a nice representation of it, but unless you're using BERT that is for named entity recognition. Sorry, yeah, there are different use cases, there are different applications.
For the sentiment analysis pipeline, do you know? I'm just kind of wondering, can you just use the BERT embedding for other purpose? Can you fit I assume you can just take that and put it in the logistic regression as well.
Yeah.
So have you ever kind of played around with that?
I have. I've actually used this. So that classification token has, ostensibly it has a representation that includes the entire sequence, and you could use that for whatever, right? Yeah, and I've used it in the same way that you might use a document level representation. I don't necessarily think that's probably not the best way to do it. There's BERT models that are particularly for these like longer sequences that might do a better job of that. But yeah, the representations are useful on their own as well. In fact, I think that pipeline uses that classification. I'm not sure. Actually, I'm not going to say that. Any other questions? Cool. Thank you very much. Thanks, everybody.